students, welcome back to our course Environmental Modeling and Simulation. Today we'll continue our discussion of a model applied in a dairy farm using empirical approach. Briefly, empirical approach is built upon all that we have studied so far in the course, how to write ordinary differential equations to model a system. And as a reminder, this is the paper that we are looking at, and it's a recent paper, recent at the time of recording. And the target of this paper was UK dairy farms in UK, specifically the slurry tank that receives the wash water, the wastewater from the dairy farms. We talked about the assumptions, we talked about the basic theory that we already know prior to modeling of how antimicrobial resistance spreads from a sensitive microbe to a resistant microbe in a system, a complex system like a slurry tank. We did this in the previous lecture. In today's lecture, we are going to write the model, the empirical model. Briefly, it's just going to be a mass balance. Mass balance that accounts for incoming slurry, outgoing slurry, and any kind of reaction happening inside the tank. The reactions happening inside the tank, as we discussed in the last lecture, include gene transfer, horizontal gene transfer, which will confer resistance, antimicrobial resistance to a sensitive microbe, sensitive bacteria. This will happen only when arrested and sensitive bacteria interact, and we talked about this little bit in detail in the previous lecture. The other thing is natural death. This is another natural death of both sensitive and resistant microbes. We are also going to talk about the logistic growth of microbes, but it is going to be modified using a Hill function to account for the bactericidal, microbicidal activity of antimicrobials and antibiotics. Okay, we ended the previous lecture discussing how the volume of the tank is not constant, it changes with time. And I wrote a very simple model. I wrote a very simple model denoting how the volume changes with time, which is Vt, which is volume at a given time, is equal to initial volume plus incoming slurry, volume increase due to incoming slurry, minus volume reduction due to outgoing slurry. So, this is influent, this is effluent. How is this going to change the concentration of bacteria, antibiotics in the slurry tank? Since the volume is changing, remember concentration. To find the concentration, we need to account for both the flow rate, the rate at which a contaminant is coming in, and the volume of the tank, the rate at which the volume of the tank is changing. Both need to be accounted for to find concentration of any antibiotic, antimicrobial, bacteria, whether resistant or sensitive, inside the slurry tank. Now here, Q is changing, V is changing, both are changing with time. So, both need to be accounted for. So, very briefly, I want to start with something very simple, dC by dt. When we do mass balance, we are very interested in dC by dt. Here, C depends on both the flow rate of the contaminant that we are interested in, whether it is a kind of bacteria or a kind of antimicrobial, and the volume of the tank, which is variable, it's not constant. So, remember I told you that when we talk about dm by dt, you need to account for both C and V in cases, especially when V is not constant. We are going to do that here. Here we can say dC by dt is basically how flow is changing with time, how volume is changing with time. Both need to be accounted for. So, instead of being dCV by dt, which here in case is product, we are interested in the rate at which flow is changing and the rate at which the volume of the slurry tank is changing with time. Okay, so let's expand this using basic differentiation that we know. So, this is basically doing differentiation of a fraction. So, the denominator becomes square and then derivative of numerator multiplied by denominator minus derivative of the denominator multiplied by numerator. Okay, so this is what we get. Now, notice here we need to know the rate at which V is changing with time. So, we need dV by dt, and we need to know the rate at which the flow is changing with time. So, we need dQ by dt. We need both of these terms, we need to put them in here, and then we will get dC by dt for any given kind of contaminant, the rate at which the concentration is changing with time. Now, notice dQ by dt is very easy to figure out. dQ by dt is any kind of reaction happening in the tank plus influent minus effluent, right? Now, any kind of reaction can be accumulation or decay, and we are assuming, this is another assumption in the model, that any kind of reaction, whether it is horizontal gene transfer or other processes that are happening, they are first order. So basically it will be some kind of function multiplied by qt, and then we have the influent minus, here we need to talk this will come into the picture. So we'll have the rate at which omega t is changing with time. Okay, so this will give us dq by dt. Okay, I should write q better so that you don't confuse it with phi. So this is what we get. Now when we take this and we input it here, and we also understand that we also derive this system, this equation that we have to find v dash t. What we will get is a very long dc by dt, which is dc by dt. Now C here is concentration, let me write this down. Concentration of some kind of bacteria, microbe, whether resistant or sensitive. It could be concentration of a bacteria, that antimicrobial, that is bacteriolytic, that is bacteriostatic, or that relates to multi-drug resistance. The bacteria microbe could be sensitive, or the resistant can be all of them, right? Or so dc by dt will be equal to phi t, which is some kind of reaction happening, multiplied by qt plus I is the influent, the rate at which the volume is changing with time, minus ct, the rate at which concentration is changing. Omega dash t, remember, it pertains to the rate at which the slurry is being removed from the tank, divided by volume of the tank at any given time, minus ct, concentration of whatever we are targeting, rate at which influent is changing with time, minus rate at which effluent is changing with time, divided by Vt. So this is what we will get. Briefly, it will be phi t Ct plus influent Vt minus Ct E dash t divided by V dash t. Okay, we are going to get equations for all of these using the system. Now we need to understand what phi t looks like for each of the system. Okay, I told you that the logistic growth model will have a Hill modification, Hill function to modify it. We are going to look into that. We are also going to look into the death rate. So death rate we are assuming for sensitive bacteria, for resistant bacteria, in fact for bacteria is going to be constant because of natural causes, unless they are dying because of antimicrobial activity, which will be included in the logistic growth model. Okay, so in case when they die because of antimicrobial induced death, now for antimicrobial induced death rate, what we are going to do is we are going to use the Michaelis-Menten kinetics. Towards the end of this course, we are going to talk about Michaelis-Menten kinetics and how it is very useful whenever we talk about substrate transformation, substrate modification. So you're going to get at least one more lecture on Michaelis-Menten kinetics. For now, I'll just show you how it will look like. The rate at which the antimicrobial related death will happen will be rate at which, so this will be equal to rate del L, the concentration of antibiotic, which is Al, is this bacteriolytic, microbial-lytic, MICL, I'll tell you what these are, plus Al. So this is very, it's just parallel with Michaelis-Menten kinetics. Now del L is the death rate at which this particular lytic antibiotic, beta L or Al, how you put it, antimicrobial, which does bacteriolysis, kills at MIC. MIC is minimum inhibitory concentration. It is the minimum concentration of antimicrobial that is required to kill a sensitive bacteria. So, if MIC L is for this particular bacteriolytic antimicrobial. So, we have three categories of antimicrobials, remember, bacteriolytic. So, L, and then we have S, which is for bacteriostatic, and U pertains to multi-drug resistance. So, for bacteriolytic, and same will be true for bacteriostatic, MIC would be different. And in this paper, they noticed that in the literature, the MIC for each category of antibiotic, antimicrobial varied, and they use that range in their sensitivity analysis, which we'll discuss later. AL is the concentration of antimicrobial in the slurry tank that we are talking about, in this case bacteriolytic antimicrobial, divided by MICL plus AL. Okay, now let's write the equations. So, let's look at the mathematical model. We will have 6 equations. Now, these 6 equations are coupled, which means they are not independent. They have variables that belong in other equations. 2 of the equations are about concentrations of bacteriostatic and bacteriolytic antibiotics. So, one is for AS and AL. So, AS is antimicrobial that has bacteriostatic activity, stops the growth of new bacteria, and AL is for antimicrobial which causes cell lysis, which kills the cell by breaking the cell apart. And then of course we have U. Now please understand what U is. I have been talking about the third kind of antimicrobial so far. Basically it is when the bacteria can be killed by a range of methods. Antimicrobial can do both or either. So, we are only going to look at these two, AS and AL. And then we have 4 different equations. So, these are 2 equations. We have 4 different equations for susceptible bacteria, which is susceptible to all. Then we have bacterioresistant RS, which is resistant bacteria to bacteriostatic. So we have S, which is sensitive bacteria. Then we have our S, which is bacteria that are resistant to bacteriostatic antimicrobials, which is AS. Then we have our L, which is resistant to AL, which is antimicrobials that cause cell lysis. And then we have multi-drug resistant bacteria, which are resistant to both kinds of antibiotics, resistant to AS and AL. So U is some intersection of AS and AL, resistance to AS and AL. Okay, so let's start with the equations for antibiotics. The equation for antibiotics will look like this. So dAs by dt, rate at which the bacteriostatic antibiotic is changing with time, is this. This is inflow minus concentration. So, we are talking about now first order kinetics, degradation of antibiotic. So, this is degradation. It is a first order degradation, notice, and that is why it is multiplied to AS plus change in the concentration of antimicrobial because of the change in the volume of the slurry tank. Okay. Now, we can write similar equation for bacteriolytic antimicrobials, dAl by dt. So, I am not going to repeat that. This is one and this one will be the second equation. Now, let us look at the ordinary differential equations that we can write for the 4 kinds of bacteria, sensitive, RS, RN and RU. Before we get there, look at what is happening here. We have inflow, we have outflow, volume change. That outflow is basically changing the volume of slurry. And then we have the accumulation or degradation happening, which is first order. Okay, so for ODE, ODE is ordinary differential equation for the bacteria will look like this. We'll have 4 equations here. Let's start with the sensitive bacteria, ds by dt. So again, we need, remember we have discussed this in the previous class, we need a growth term, and the growth term we are going to use will be logistic growth with Hill function, modified logistic growth. So R 1 minus n by u, this sort of reminds you of logistic growth, yeah? Well, ES S, this is where Hill modification comes in. But let me just clarify, this is modified logistic growth. So this part should sort of resemble the logistic growth in your memory. Then we have horizontal gene transfer, and we have done this modeling in the last lecture. This will look like sensitive bacteria. KBS, that's what I get, K beta S, K beta L, K beta U is what I used as constants in the previous lecture. Here let's just remove the K, let's just stick with beta S, beta U and beta L. Genes that confer resistance to AS, which are bacteriostatic antimicrobials. Genes that confer resistance to AL, which are bacteriolytic antimicrobials, and genes that confer multi-drug resistance to both bacteriostatic and bacteriolytic. And then we need to account for inflow, the rate at which susceptible bacteria are coming inside the tank, which is going to be the rate at which the flow is happening, 1 minus rho. And I'll tell you what these terms are. Minus the rate at which the volume is changing because of the effluent, minus natural death, which we decided is going to be constant. So constant death rate del S for sensitive bacteria, minus sensitive bacteria will also die because antibiotics, antimicrobials are present in the environment. So this is where we talked about using Michaelis-Menten kinetics, and I showed that in the previous slide. No, not in the previous slide, in this slide. So this is what we are going to use. So this is natural death. Let me highlight what each of these terms mean, because this is very important when you're doing empirical modeling. You write all the phenomena and you try to understand the best way to model these phenomena. So this is modified logistic growth. The modification is here and we'll talk about it. This is known as the Hill's modification. And then we have horizontal gene transfer. We have 3 different kinds of bacteria, resistant bacteria transferring their genes to the sensitive bacteria, which give them resistance against AS, AL and MDR, multi-drug resistant. Then we have the inflow, which also accounts for not just the rate at which the inflow is changing, but the rate at which the volume is changing because of the incoming slurry. And then the rate at which the volume is changing because of outgoing slurry, natural death of sensitive bacteria, and the death of sensitive bacteria because of antimicrobial resistance. Now let's look at the rate at which the concentration of resistant bacteria will change with time. Let's start with dRs by dt, which is the bacteria that is resistant to bacteriostatic antimicrobial but is still sensitive to bacteriolytic antimicrobial. Okay. Very similar, again we'll have a Hill modification in the growth rate. So this is modified logistic growth. In the next lecture we'll discuss more in detail each of these modifications, don't worry. So this is again horizontal gene transfer. Here notice the minus sign, because every time a sensitive bacteria turns into a resistant bacteria, the sensitive bacteria ds by dt is going down, sensitive bacteria number is going down, but resistant bacteria number is increasing. Again, very similar to what we saw in the first system. So we have influent, inflow, we have volume change, we have natural death of resistant bacteria, even if antibiotics cannot kill them, static antibiotic cannot kill them, but they are still dying a natural death. And bacteriolytic antibiotics can still kill them. So resistant bacteria that are resistant to bacteriostatic are still sensitive to bacteriolytic. So we need to account for that. So notice here we are using L because the RS is still sensitive to bacteriolytic antimicrobial. So we have to account for del L, AL, MICL. But it is the death rate of RS, not of S. Okay, so RS and S behave very similarly. The terms are quite similar, easy to understand. We'll talk about the Hill modification in detail in the next class, but let's finish writing our equations today in this lecture. Then we have the rate at which bacteriolytic bacteria that are resistant to bacteriolytic antimicrobials are changing with time. Again, we'll have some very similar principles. A modified logistic growth model. This is L. Okay, now before I go further, I want to spend some time looking at the modified growth model for modified logistic growth for both RS, S and RL. So I told you that this is the modified logistic growth model with Hill modification, Hill function, and we'll talk about that in next lecture. But when we are talking about the two kinds of resistant bacteria, RS and RL, we also have this 1 minus alpha S and 1 minus alpha L happening here. This is showing that there is some kind of cost that the bacteria is paying for having additional genes that inhibit its successful growth. So we know this is a thing about bacteria, that when they acquire excessive genes, even if it gives them advantage in competitions, advantage in harsh environments such as slurry tank that has antimicrobials, it does have an energy cost on the maintenance of those extra genes, in replicating the extra genes, which will slow down its growth rate. We know resistant bacteria grow slowly compared to the sensitive bacteria. Okay, finally, let's write down the equation for dRu by dt, which is the rate at which MDR, multi-drug resistant bacteria, are changing in the slurry tank. So again, the multi-drug resistant bacteria also need to pay a fitness cost. So again, that correction 1 minus alpha u is there. I hope you realize how well you need to understand the theory to write these equations. But once you do, once you know your ODE, very easy. So this is your modified growth model. And then we are talking about the horizontal gene transfer. So far very similar to the equations we wrote for S, RS and RL in terms of the inflow, change in volume, the natural death rate, and even in logistic growth model when we also understand why we have this fitness cost here. The interesting thing that's happening is how the horizontal gene transfer is differentially affecting the growth rate of each kind of bacteria. So let's take a look at that. So if we look at RS, which is bacteria resistant to bacteriostatic antimicrobial, we notice that its number, its growth rate increases plus RS beta SS, which means RS increases every time a resistant bacteria RS gives its resistance to a susceptible bacteria governed by the rate beta S, but it loses minus RS beta LRL this term and minus beta URURS. And I want you to think about it, like pause this video and think about it, why there is a minus sign here. There's also a hint about what's happening in case of RL. Every time a sensitive bacteria interacts with the bacteria RL, the growth rate increases. So we have a plus sign here. But here we have RL beta S RS minus, beta URU minus. Now in case of multi-drug resistant, we have something even more fascinating happening. Multi-drug resistant increases when this interaction happens, and also when a multi-drug resistant bacteria RU interacts with the sensitive bacteria, with the bacteria RS and RL. Let's look at the second part first because this is fascinating. What's happening here? So remember, RU is basically a bacteria that is at intersection of RS and RL in this area. So it is resistant to both bacteriostatic antimicrobials and bacteriolytic. So even RS can acquire RL's resistance and become RU. So every time, so to become RU, to become multi-drug resistant, here the three major ways are that a multi-drug resistant bacteria interacts with a sensitive bacteria. Here we have beta U and then we have 2 RU. So this is what you are seeing here. Okay, so this is the first term here. The second is a multi-drug resistant bacteria RU interacts with RS and something similar happens. And similarly, RU interacts with RL and makes it multi-drug resistant either. So all these three are here. Now for why we have this additional term here and why we have subtraction here, this is something we'll discuss more in detail in the next class. Meanwhile, do take time to think about it, why this is happening. If you are eager and more curious, you can even check it out in the paper. Remember, the paper we are discussing in this lecture, in these lectures is this. Okay students, this is all for today's lecture. In the next lecture, we'll continue our discussion. We'll also look at the results. Before I move on, I want to remind you that here we have 6 equations. 2 of them are for antibiotics, AS and AL. 4 of them are for 4 different kinds of bacteria sensitive, RS, RL and RU. And 6-dimensional equations are sort of hard to analyze geometrically. Geometrically, we can do 2D very well, 3D really good, but anything more than that is really hard. So in this particular system, we are going to use MATLAB. Well, we are not going to use MATLAB, but the authors used MATLAB, and I'm going to directly show you the results in the next lecture once we are done discussing the rate equations for different kinds of bacteria. Okay students, this is all for today's lecture. Thank you. See you in the next one. Goodbye.